Hi, everyone. We are happy to have met Weinberg today, who is going to tell us about recent developments in combinatorial auctions. Matt.
Thank you. So I'm going to talk actually about a couple papers. The first one is joint with Mark Braverman and Jiaming Mao. The second is joint with Linda Tsai and Clay Thomas, and the third is with Seper Asadi, Rishi Kandabakar, and Raghavan Saxena. There's actually a fourth paper in the abstract, but I think I realized that was too ambitious to try and cover all of that. But I'll just quickly mention the fourth one was joint with Tomer Ezra, Michal Feldman, Eric Neiman, and Inbal Togum Cohen. But I think I cut that one due to time and because more of those authors are already part of the seminar. What I want to do in the talk, I'm actually going to spend a decent amount of time trying to give, I guess, like how I view the landscape of combinatorial auctions, which hopefully is also consistent with how people in the audience view it. And then I'll describe two sets of results. So the first set is going to be in the communication model. The second set is going to be in the computational model. The first set of results will look a little bit more like a classical communication complexity lower bound. The second set of results is going to propose a solution concept and try and explain why this solution concept resolves some of the weirdness between the interaction between computation and incentives. So let me start with this, and I do want to disclaim, I know there's actually a lot of people in the audience who have worked on combinatorial auctions, so I'm just trying to give the part that's relevant to the result I want to share. So I just want to give the part that's the part of the history that's relevant to the work I want to share today. And so it's a little bit of a focused view towards that. Okay, so just to make sure we're on the same page for the title. So there's n bidders and m items. Each bidder has a valuation function. In the combinatorial setting, they have a valuation function that maps fully sets of items to their value for that set. The bidders are going to participate in some protocol. That protocol might be interactive, or they repeatedly send messages back and forth between the auctioneer. And then at the end of the protocol, the auctioneer is going to decide for every bidder, what set of items do you get and how much do you have to pay. And the goal for this entire talk is just going to be to maximize the welfare. So the auctioneer's goal is to maximize the sum over all bidders, their value for the set of items that they get. And alpha, then the entire talk is also going to consider approximation. That's just getting a factor of what the optimum would be. And then the auctioneer would like a protocol that's truthful. Okay, so just to be really clear, truthful means that for all valuations, no matter what your value is, no matter what the value of the other players, it's in your interest to follow the protocol. And the formal definition of that, it's an ex post Nash. So it's Nash equilibrium. As long as everyone else is playing consistent with some valuation function, it's in your interest to play consistent with your true valuation function. Okay, so the main question, I would say the high level question that motivates this research area, again, at least for the style of works that I want to talk about today, is are truthful mechanisms as powerful as algorithms? Okay, so is it the case that you can do everything that you can do with an algorithm? Can you also solve that problem with a truthful mechanism? And combinatorial auctions are a really natural testbed for this, because the problems are very natural in a strategic setting. So combinatorial auctions are actually run in practice with strategic bidders. And there's an obvious algorithmic counterpart where you just remove truthfulness and say, can you do this with an algorithm? And those problems actually have been studied even before combinatorial auctions, but in different contexts. Okay, and for the story, there's actually not a clear yes or no answer. So within combinatorial auctions, I would say it turns out that the right way to ask the question is just when are truthful mechanisms as powerful as algorithms? So let me just give you some examples. So, okay, so there's these seminal works, the VCG mechanism from Vickery, Clark, and Groves, which phrased in like a computer science language, I would say is that using n+1 black box calls to an optimal algorithm for whatever valuation class you want to solve the problem for, you can also get an optimal truthful mechanism for that valuation class. So what that means is that it is the case that if you want to exactly maximize welfare, then any setting that you can do with an algorithm, you can also do it with a truthful mechanism. And the catch, the reason that we normally don't consider this a completely solved problem is that for basically any interesting class of valuation functions, it's both NP hard and requires exponential communication to actually run this algorithm. So the answer is just you can't do it with an algorithm. You also can't do it with a mechanism. And then there's also a series of works that I would say if you insist on your algorithm working for every possible monotone valuation, so if you want to work it for the most broad class, then there are algorithms that get a 1 over root m approximation, and that's the best that you can do with poly communication. There's also a truthful mechanism that matches the same guarantee. So what I would say is the takeaway from this is that if you insist on being exactly optimal, or if you insist on working for all monotone valuations, then in those cases the answer is yes. But I would say that's just because you can't do very much, and so as a result, the mechanisms that you can use are as good as the algorithms. There's another series of results that considers, let's say, when the valuation functions are submodular. And let me put both of these up. I'll focus on the set at the bottom. The results at the top are just in a slightly different computational model. But at the bottom, we have the following results. So it says that if the valuations are submodular, then there is a natural computational input model where you can get a 1 minus 1 over e approximation in polytime with an algorithm. But there's a series of papers, and the one I've cited is the conclusion, which shows that actually you can't do the same in that same model with a truthful mechanism. So in fact, you still can't do better than the same 1 over root m. Okay, so that's when valuation functions are submodular in this pretty natural computational model. Okay, so how I would summarize my understanding of the state of affairs is that in the computational model, truthful mechanisms are just as powerful as algorithms in, I would say, these extreme cases where either you insist on working for all monotone valuation functions, or you insist on getting an exact solution. But in kind of like the domain that approximation algorithms has decided is realistic, where you make some assumptions, such as being submodular, and you're okay with approximation, then it seems like they're much less powerful. So what I want to point out is that there's something a little bit funny about the state of affairs. And I just want to remind you, so at the top, I have just recited the same hardness. But going on in parallel with this, there was also a series of papers that showed that you can get a truthful 1 over poly log now approximation for submodular bidders. And these auctions, they're a little bit more complicated than posted price mechanisms, but they are basically posted price mechanisms. So what I mean by that is you post a price on each item, you visit the bidders one at a time, the bidder purchases their favorite set at these posted prices. Okay, so they're definitely more complicated than that. There's some statistics gathering at the beginning, and there's maybe you repeat the posted pricings a few times and pick one that works well. But this is really the underlying mechanism that the bidders interact with. And for all of these, the prices can be computed in polytime. All the pre-processing is done in polytime. And okay, so I know for a lot of people in the audience, this is not the first time you've seen this, so you kind of already know what the catch is going to be. But if this is the first time you're seeing this, it initially probably seems like something funny is going on. There might be a bug in one of these results. That's not the case. And the catch that reconciles that both of these can be true is that these posted price mechanisms, even though everything that the mechanism designer does is in polytime, they compute the prices in polytime, they do all the statistical gathering in polytime, this operation of ask the bidder to purchase their favorite set at the posted prices. So that operation we call a demand query, and those are actually NP hard in the model of the hardness result at the top. So that means is that these mechanisms are technically not polytime in the computational model because they're asking the bidder to solve an NP-hard problem. So what I would say is that it feels to me like there's something funny going on between truthfulness and computation. And maybe independently of how you feel about that reconciliation, we should, as a research community, also care about lower bounds which rule out posted price mechanisms. And the point is just that computational lower bounds in this model don't, because these posted price mechanisms aren't technically polytime, and these posted price mechanisms are already beating the lower bounds exponentially by than what these lower bounds say you can't do. Okay, so what I want to do now is I want to give you one more example of this one. I think is I would be more confident stating this one is really weird, and it's not just a matter of choosing between different models of computation. So let's consider, so this is a related combinatorial public projects problem. For one bidder, the problem is very simple to state. So there's m items, there's one bidder, the bidder can take at most k items, and the bidder has a submodular valuation function over the items. Okay, so from again, the game theory is very simple. There's one bidder, and our interests are aligned. The bidder wants to maximize their value, and I would like to maximize welfare. I would like to maximize the bidder's value. Okay, so you can ask, what is a mechanism that is truthful, maximizes welfare, and is computationally efficient? And the obvious mechanism that it seems like to use here is you just tell the buyer, pick your favorite set of size k for free. Our interests are aligned. There's no other bidders. That seems like the obvious thing to do. And the catch is that, okay, you're just asking the bidder to solve an NP-hard problem. And so the buyer actually can't do that in polytime. So you'd say, fine, okay, so this mechanism does not maximize welfare and call it computationally efficient. An algorithm can't even do that. So it would be silly to say that just tell the buyer to do it. So next question I would ask is, okay, so is there a mechanism that's truthful, approximately maximizes welfare, and is computationally efficient? And here you might say, okay, let's just use the same mechanism. So just say, I'll tell the buyer, you can take any set of size k that you want for free. Just run in polytime, run whatever heuristic you want. You can go for it. And with an algorithm, a 1 minus 1 over e approximation is possible. And the catch, so the weird thing about this is that this mechanism, it sounds truthful, right? You tell the buyer, pick any set of size k you want. The buyer will pick any set of size k you want. But when you actually go and you kind of map what that means into the formal model is you're supposed to say for every valuation of the buyer, what exactly is the set they're going to purchase. That mapping is supposed to be in polytime, and that mapping is supposed to be incentive compatible. So that mapping is supposed to have the property that the buyer prefers what they take to what they would have taken with any other valuation. So if you really port this into what does it mean to be truthful, you have to explicitly look at what does the revelation principle do to the mechanism. And the catch is that what will always happen, or what will happen with this 1 minus 1 over e approximation is, the buyer, it's not truthful because the buyer could have done more computation. There is some better set out there that the algorithm didn't find. The buyer, can't find it in polytime, but they could have done more computation. And there's even a formal result, from 2008, which says that actually, if you really look at what mechanisms are truthful for the buyer, and you look at all of the mappings that satisfy that, then the best one of those that runs in polytime actually only gets you a 1 over root m approximation. Okay, so what I would say is that this to me seems like a weirder example of interaction between computations and incentives, where I would say if you ask me conceptually what's going on with question 2 and answer 2, I would say answer 2 to me sounds like a truthful mechanism that approximately maximizes welfare and is computationally efficient, because what I would really expect is if I use that mechanism, I am so confident that the buyer would get a 1 minus 1 over e approximation. So it might not satisfy the formal definition of truthfulness that we usually use, but I would say in terms of how robust is that guarantee, I would say it is as robust as a guarantee that we normally get from truthfulness. Okay, so that's all of the setup for kind of like what's the state of affairs, and in particular, what are the things that were motivating, like motivating me to think about these problems. And so the focus of the rest of this talk is to kind of address this weirdness in two directions. So the first direction is just to observe that all of the weirdness that happened on the previous slide and the examples that I said, all of that weirdness is coming from computation. So none of that weirdness happens in the communication model. The reason for that is that, in particular for posted price mechanisms, you can state the set you would like to purchase. That's just telling the designer what's the set you would like. And it's the same issue in the second one. You can state your favorite set in low communication. The second thing that I want to talk about is a different solution concept. We were calling it implementation in advised strategies. And we actually learned from Moshe that it's equivalent to a solution concept that they had looked at a long time ago. So I'll introduce the solution concept. I'm not going to get into why it's equivalent, but it is equivalent to something that had been studied before. And you should think of this solution concept as being really, really robust in the sense of it's going to be really permissive. So implementation in Nash or in dominant strategies is a robust solution concept because you're prescribing extremely reasonable behavior for the bidders. But there are more robust solution concepts where you just say something good will happen as long as they don't do something undominated. And this is going to be even more permissive. It's going to allow the players to play dominated strategies, and the mechanisms will still get some guarantees. So those are the two directions that we're going to go in. And I'm going to transition now to talking about the first results. Oh, sorry. I'm almost going to do that. So I don't know actually if there are any economists in the audience, but I have given a version of this talk to an economics audience. So I felt obliged to say something of the following. So I know that there's like this caricature of computer scientists, exactly like what's going on in this comic, where people think that computer scientists love approximation guarantees, and we get super excited, in this case, about narrowing down something, 642 to 639. And I'm not contesting that caricature is sometimes true, but I do want to highlight that that's not what's going to go on in this talk. So I am going to claim that I'm excited about improving something from 3/4 to 3/4 minus 1/240. But again, the reason that I'm going to be excited about that is just because those two numbers are different. Because one of those is the best that you can do, in one model, and one of them is saying that you can't do that well in a different model. So I just wanted to give that disclaimer. Okay, so I don't know if anyone would like to quickly pause and ask questions, but now would be a natural time because I'm going to shift away from the background and story and start talking about the first set of results. All right. Okay, so I will keep going. Okay, so let me again quickly remind you what problem is communication complexity solving. It's just that posted price mechanisms do run in polynomial communication. So what that means is that if you can prove communication lower bounds on truthful mechanisms, these actually do rule out good posted price mechanisms. And again, independently of whether you prefer the computational model or the communication model, I would just say it is true that lower bounds on what you can do with communication efficient truthful mechanisms, they are doing something that you can't do in the computational model, which is addressing posted price mechanisms. Okay, so the state of affairs, so everything I was telling you about before, all of those separations were for the computational model. And for the communication model, prior to the work that I'm going to show you, there were actually, there's an asterisk, but for, that there were no known separations between what you can get with poly communication with a truthful auction and poly communication with a non-truthful auction. And so what that means is that there's no known lower bounds that actually invoke truthfulness, again, for the lower bounds on what you can do with poly communication. And still, there's a really large gap between what you can do in terms of positive results. So what I would say is, to me, the state of affairs means that this is just something that we should be studying more. So for the entire duration of the communication complexity portion of the talk, the classes of valuation functions that I want to study are XOS valuations. So this is, if you haven't seen them before, it's a maximum over additive functions or a maximum over linear functions. And that just means that there exists a list of additive functions. And when you pick a set and you decide what your value is for it, you look over all the additive functions, you see what's the additive function on that set, and then you take the maximum of these. Okay, so what's the state of the art in terms of what we know how to do for XOS valuation functions? So in terms of, this is all in the communication model. So in terms of algorithms, I wrote this in a super precise way, FIGA's result, just to emphasize that we really understand what the approximation guarantees are that you can get for algorithms. So this approaches 1 minus 1 over e, but in fact, for every n, we know exactly that you can get this 1 minus 1 minus 1 over n to the n. The state of the art I mentioned is there is a randomized 1 over log m cubed approximation with the truthful mechanism. But actually, if you insist on being deterministic with the truthful mechanism, then again, the best we know how to do is 1 over root m. So the main thing I want to point out here is that for n bidders and m items, these truthful mechanisms are not constant factor approximations. And for deterministic mechanisms, it's actually quite far. But we have, optimal constant factor approximations for algorithms. And the other thing I want to zero in on is when there's only 2 bidders, what does the state of affairs look like? So for 2 bidders, there's a 3/4 approximation algorithm. That's deterministic. That's the best that you can do even with randomized. That's just plugging in n equals 2 to the earlier result. But the best thing we know how to do with a truthful mechanism, we actually don't know how to beat a half approximation. Okay, so again, the difference between 3/4 and a half, those are 2 constants, who cares? But a 1/2 approximation, that's actually really trivial. So it's not like we have this fancy truthful mechanism that can do something interesting, but it gets a half instead of 3/4. The best thing we know how to do is just say, take all the items, bundle them together, run a second price auction. That's the only thing we know how to do with a truthful mechanism for 2 players. So even with randomization, we don't have anything better. Okay, and the main challenge for kind of like getting better lower bounds, so I'm talking from the perspective of, I don't think it's the case that in this model, truthful mechanisms can do everything that algorithms can do. So what's the challenge in proving lower bounds? So the challenge is that most of the prior work, not all of it, I'm going to tell you one different direction, but most of the prior work tries to proceed by saying, let's characterize all truthful mechanisms. And then once we characterize them, we'll show that that class of mechanisms can't do anything very interesting. And so there is a precedent for this being successful in some special cases. So there's the main class of algorithms that have been studied through this lens are what are called affine maximizers. I'm not going to get into the definition other than to tell you that there are truthful auctions that are not affine maximizers. And in particular, posted price mechanisms are not affine maximizers. And so posted price mechanisms, especially the randomized ones, are getting beyond these lower bounds. And the point, I think the main thing I learned, from trying to read these papers, that it might not be a tractable approach to try to characterize all truthful combinatorial auctions, especially subject to restrictions such as submodular or XOS. That this might be an intractable agenda, and so a different approach would be good. So the different approach was introduced in 2016. So it's a recent paper of Shahar Dobzinski. And so I'll try to spend some time introducing that approach, saying kind of what it means, what problems it encourages people to solve, and then telling you what we did on that. Okay, so again, so the point of this slide and what's coming after is to try and prove communication complexity lower bounds that specifically apply to truthful mechanisms, but that do not also apply to regular algorithms. So the starting point is this concept called the taxation principle. So the taxation principle says that every deterministic truthful mechanism can be viewed in the following way: as a function of the other bidders' valuations. This presents a menu to each bidder I. And what that menu does is it lists for every set S, it says what is the price that bidder I would have to pay in order to get set S. So let me just give you one example of this being implemented. If you think of the second price auction, what is the menu presented to bidder I? So one thing they can do is they can get nothing and pay 0. Another thing they can do is they can get the item and they can pay the highest bid of the others. So that's the menu presented to bidder I as a function of the other bidders' values. Okay, so the taxation complexity, so this was a framework introduced by Dobzhinsky, is the maximum over all bidders of the log of the number of distinct menus. Okay, so let me go through what exactly does that mean. So if you have a second price auction and the bids are integral, so every bidder has a value that's an integer from 0 to n, then I as a bidder, there are n+1 different menus that I might see. So what I mean by that is every menu I see is of this form. At the top, you can either get the item and pay the maximum value, or you cannot get the item. And depending on the maximum value, this option is going to change. And so what that means is that there's n+1 different menus that you might see. So the taxation complexity is log of n+1. As another example, if I want to fully run the VCG mechanism, and there's 2 bidders, and they each have valuations in some set V, then there's a different menu for me for every possible valuation of the other bidder. That's going to show me a different menu. Okay, and the reason for that is if I just write out the formula for what's the price that I have to pay for set S using the VCG mechanism, it's going to look exactly like this formula at the bottom. And that formula is different. If there's any set in which 2 valuation functions differ, then the menu is going to be different. Okay, so this is different than we normally think of. So there's this term called menu complexity. That's different than this. Menu complexity is the number of options on the menu. This is looking at the number of distinct menus. Okay, so in general, so this is the same example that I've seen when I saw Sahar give a talk on this. So I just wanted to emphasize it's, I definitely stole the example from him, but it points out that it's not always the case that for every truthful mechanism, there's a relation between communication complexity and taxation complexity, or for every algorithm. So in general, there are procedures where the communication complexity can be significantly less than the taxation complexity. So somehow the mechanism concludes without ever learning what was the menu it presented to the bidders. Okay, so here are just 2 facts to help understand this. So if you do VCG with 2 bidders and they both have gross substitutes valuations, here are just 2 facts. So there are doubly exponentially many gross substitutes valuations. So that means that because there are doubly exponentially many possible valuations, the taxation complexity is exponential. On the other hand, we know several procedures that will let you run VCG for gross substitutes valuations in polytime. So one approach is using this configuration LP where you can solve the LP and the optimal solutions are integral for gross substitutes. Another approach is you can use your favorite procedure for finding a well-rationed equilibrium, and that will also run VCG. Okay, but the cool part of Dobzhinsky's framework is that if a mechanism is truthful for a rich enough valuation class, then you can relate the taxation complexity to the communication complexity. Okay, and so this is, for me, the exciting part of this is that this is a way to prove lower bounds only against truthful mechanisms, because these claims do not hold for all protocols. Okay, so for, in particular, the first result he shows is that if M is truthful for all monotone valuations, then the taxation complexity lower bounds the communication complexity. If M is truthful for XOS valuations, so this is the one that's most useful for us, then the taxation complexity lower bounds a polynomial function of the communication complexity. And then finally, there was a bonus result that he showed, which is going to be even more useful for us, is that if you look at mechanisms that are truthful for 2 XOS bidders, then there's this additional result, which says that the simultaneous communication complexity also lower bounds the taxation complexity. So what I mean by that is that the simultaneous communication complexity of a, sorry, I shouldn't have written that of a mechanism, of a, the simultaneous communication complexity of a problem. This is the, simultaneous protocol is one where each bidder sends exactly one message simultaneously. Then the protocol terminates and the designer decides how to allocate. So what the third line is saying is that if there is a good truthful mechanism, then it has low taxation complexity by bullet 2. And there is a simultaneous protocol with lower communication than that. Okay, so the main thing I want to take away from this is that through these series of reductions that are in Dobzhinsky's paper, here is now a feasible path towards separating what you can do with truthful polycommunication protocols and non-truthful polycommunication algorithms. So if you can get a certain approximation guarantee with a truthful deterministic mechanism for 2 bidders, then this series of claims says that you can get the same guarantee with a simultaneous protocol as well. However, there's lots of examples. We know that there's lots of examples of problems where the best approximation ratio you can guarantee or the best protocol has to be interactive, and you can't solve the same problems with a simultaneous protocol. So as in terms of a pure communication problem through Dobzhinsky's framework, the goal now is to separate what you can do with simultaneous communication protocols and what you can do with interactive communication protocols, specifically for 2 bidders for XOS valuation functions. That's the problem we're left with. Okay, so now the first result I want to tell you, now that I set up all of that framework, is basically providing this separation. Okay, so very formally, what's the problem that we have to study? So now I'm just resetting, I'm defining a communication problem. All of the previous 15 minutes was just motivation for why is solving this problem actually going to say something about truthful mechanisms. But here's the communication problem, just to be really clear. So there's 2 bidders, Alice and Bob. They each have a valuation function. That valuation function for our case is going to be, XOS. And specifically, the problem that they need to solve, there's 2 ways you can ask it. The first one I'll call the search problem. So your goal is to actually output a set, and you would like that set to maximize the value that Alice gets plus the value that Bob gets for its complement. Okay, so the goal is you have to actually find a set that gives you good welfare. There's another way you can ask the question, which is as a decision problem, which is you can ask, is it the case that there exists a set such that Alice's value for that set plus Bob's value for the complement is at least C? And then for both of these, you can ask a approximation variant, which is you can find a set that's approximately optimal, or you can be just deciding between cases where the welfare is at least C or at most alpha C. And I want to point out kind of like one interesting fact about search and decision problems when you insist on simultaneity in the protocols. So most of us, including me, so when I learned algorithms, we learned that normally search problems are harder than decision problems. And the reason for that is that we have this really trivial reduction in mind, where we say, okay, if I can solve the search problem, then I have found a solution that is optimal. Let me just find out how good it is and see whether it's bigger than C or not. Another thing for the approximation one, you can say, okay, I found something that is promised to be an alpha approximation through the search algorithm. Let me just evaluate it and see whether that's bigger than C or less than alpha C. And the only thing I want to point out is that for that trivial reduction, if you were to really implement that in the communication model, that does require an additional round, right? So you have to run the first protocol, find the answer, and then in one additional round, you can evaluate it, okay? And so what that means is that if you insist on having a simultaneous protocol, it's actually not obvious that the decision problem is easier than the search problem. And I'm actually going to show you that for this problem, I'm going to show you a lower bound that holds on the decision problem, but that doesn't hold for the search problem. And the long reason for why that's interesting is that the Dobzhinsky's reduction applies to the search problem. So we need to show that the search problem is hard. That's going to be the end goal. But I just want to point out that interesting note about search versus decision. That's going to explain why the construction that I show you, which is simpler, is not already fully solving the problem. Okay, so it's formal statement of the main result. Let me just remind you what was already done. So there's this algorithmic 3/4 approximation and polynomial communication for two buyers that are both XOS. Then there's Obzinski's framework, which says that the goal is to prove lower bounds on what you can do simultaneously for the search problem for XOS. And the first result, and this is the one that I will overview this construction, is a lower bound for the decision problem. So I will overview that construction. I will give you some intuition for why the decision problem is hard to solve simultaneously. And that was from this work with Mark and Jiming 2 years ago. And unfortunately, the weird thing about this construction is that it actually does admit a polynomial 3/4 approximation for the search problem. And so again, what I was stating was that that is at least conceivably possible, because just because you can solve the search problem simultaneously, you still need one extra round to solve the decision problem. So you can solve that, you can get a 3/4 approximation in 2 rounds for the decision problem, but not 1 round. Okay, so this is interesting. You know, I thought that was a cool construction. It was a fun paper, but unfortunately, it has no implications for Obzinski's framework. So then the more recent results, so this is with Seper, Rishi, and Raghavansh, we were able to show a weaker lower bound, but still a lower bound below 3/4 for the search problem. And I'm not going to describe how to get to this construction from the original one. I think the most intuition that I can capture while still spending 30 minutes on the background like I wanted to is to just show you the BMW construction. And again, I just want to highlight, so in conclusion, this result is the first separation in the communication model for what you can get for any number of bidders, any valuation class, between poly communication with an algorithm and poly communication with a truthful mechanism. Okay. So now I'm going to give, it's going to be maybe 3 slides of technical stuff, just to give you an overview of this construction. Okay, so here's the idea, is the following. So for each of Alice and Bob, so remember we said you can think of their XOS valuation functions as it's a long list of additive functions, or you can think of it as a really long matrix where each row corresponds to an additive function, and then the number of rows is equal to the number of different additive functions they have. So the starting point is so the valuations are all going to be 0 or 1 for each item. So you can think of it as a big 0, 1 matrix, and they're going to be indicator vectors for random sets of size m/2. So let's just quickly go through what that means in terms of their valuation functions. So Alice's value for some set S is just going to be the maximum over all sets in her list of the intersection of that set with S. And the same thing is going to be true for Bob, except for the sets in Bob's list. If they have a long list of sets, the way they value a set S is they say, which set in my list has maximum intersection? Okay, and so then we'll just observe that what this means is that the maximum achievable social welfare is just the maximum over any list in set in Alice's list and any set in Bob's list of the union of those two. Okay, so the first construction, just to give you some intuition, is if you want to show that an algorithm can't do better than 3m/4, one thing you can do is you can let each set be uniformly random. Okay, so the starting point is you just give Alice and Bob each a bunch of uniformly random sets, and two uniformly random sets, their union is going to be roughly 3m/4. And so what this means is if you just start with this, then so far the optimal social welfare is 3m/4. And then what you're going to do to make it hard for Alice and Bob to figure out whether the optimum is actually m or only 3m/4 is you give Alice one special set that is a priori indistinguishable from any of the others, and you give Bob one special set that is a priori indistinguishable from any of the others. And this is easy because all of their sets were just uniformly random. And what you do is you say, if I want the answer to be yes, so I want it to be the case that there is good welfare, then I just make these sets disjoint. The idea is Alice and Bob will never be able to figure out which set was their special set, so they don't know which sets they're supposed to check if they're disjoint or not. And if I want the answer to be no, I'll make them the same set. Okay, and again, they'll never be able to figure out with low communication what the answer is. This is not a formal proof. The formal proof, you can reduce it from disjointness, but this is intuition for kind of like why this construction is hard. Okay, so this is the base one that shows that an algorithm can't do better than 3/4. Okay. Okay, so again, so I'm not showing you the formal reduction. There is a formal reduction. Okay, so we don't want to do that construction. We want to do something better. And it can't be uniformly random, because if we just give them uniformly random sets, then if I just pick 2 random rows, that actually gives welfare 3m/4. So I can't prove hardness better than 3m/4. Okay, so here's the construction. So it's going to have a couple steps. It's not going to be super long. It's just going to be 2 or 3 steps. So what I want to do is I just want to make their random sets. I want them to intersect a little bit more than normal. So if Alice and Bob's random sets intersect a little bit more than uniformly random, then the 2 random sets is not going to give 3/4. It's going to give strictly less than 3/4. So how are we going to have Alice and Bob draw 2 sets that intersect a little bit more than random? So we're going to start by giving Alice 1 set S, and Bob is going to get 1 set T, and these are going to intersect more than random. So they're going to intersect at m/3, but they're going to be uniformly at random conditioned on this. Okay, so this is all we have so far. There's m items. Alice has this 1 set S, Bob has this 1 set T. They intersect more than normal. Alice's sets are now going to be drawn at random so that they intersect S more than normal. And Bob is going to draw exponentially many random sets that intersect T a little bit more than normal. Okay, so whoops. Okay, so I haven't drawn, sorry. So I haven't drawn those, but what you can maybe see, even without the picture, even without going through the math, that, you know, S and T intersect a little bit more than normal. All of Alice's sets intersect S a little bit more than normal. Therefore, they intersect T a little bit more than normal as well. And then Bob's sets intersect T a little bit more than normal as well. So the random sets of Alice and the random sets of Bob, they just intersect a little bit more than normal. Okay, and so because they intersect a little bit more than normal, the union of 2 random sets is a little bit less than normal. And so far, if I were to completely stop the construction here, then the maximum welfare would be 3/4 minus a little bit. So 3/4 minus 1/108. So now what I want to do is I want to give Alice, again, 1 special set, and give Bob a special set. And I want them to be a priori indistinguishable from the others. Okay, so let me just quickly show you how I can do that. So these are 2 disjoint sets. So A0 and B0 are disjoint. And you'll notice that A0 intersects S at m/3, which is what it's supposed to do. And B0 intersects T at m/3, which is what it's supposed to do. So what this means is that if I give Alice and Bob A0 and B0, then without any communication, these just look like a random set that like any of their others, because it intersects S the way it's supposed to. For Bob's, it intersects the way it's supposed to. And if I want, and the other thing I can do is I can make the same set that intersects S at m/3 and also intersects T at m/3. So this means that, again, I have the flexibility to make a yes case and a no case a priori indistinguishable for Alice and Bob. Okay, now the main idea here is that if Alice does not know T, and she does not know T before they communicate, then A0 looks exactly the same as the rest of her sets, because she knows nothing about T. A0 intersects S just like all of her other sets, so it looks completely indistinguishable. Same thing for Bob. Bob doesn't know S, so therefore all of his sets look the same. Okay, and so there is a formal way to prove this, that there's nothing they can do simultaneously to do better than 3/4 minus 1/108. However, why this is not an interactive lower bound is because if Alice knew T, then there is something kind of like painfully obvious about A0, which is that it intersects S at M over 3, but everything that doesn't intersect S is completely disjoint from T. And that has to be possible in order to get these to be disjoint. And similarly, if we're in this other case, then this part that doesn't intersect S, all of it is contained in T. That would not happen for a random set. So the 2-round protocol that lets them solve this is in round 1, they exchange S and T, and then in round 2, they know what their special set is. But this is still a simultaneous lower bound because without the first round, they don't know which of their sets is special. Okay, so that was the intuition for the construction. Just to remind you, I told you that for the decision problem, there actually is a good 3/4 approximation. It's actually strictly better than 3/4 for this construction. And that's again because of for the search problem, there's better than 3/4. And that's because of this weirdness where it's actually possible for Alice to just propose a set. In particular, if Alice just picks a uniformly random one of her sets and says, this is the allocation, that will do strictly better than 3/4 on this instance. However, Alice and Bob can't figure out whether it's getting, it can't figure out whether it's getting, it can't figure out the welfare that it actually guarantees simultaneously. So they know an allocation that gets a 3/4 approximation. However, they don't know numerically the value that it's guaranteeing. So that's a weird thing that can happen. But again, that's the problem that we need to show is hard for Lipzinski's reduction. So what was going on in this later work was basically finding some way to put a bunch of machinery around this construction to get a lower bound for the search problem instead. And so that was the main technical stuff that took us actually quite a while to figure out how to do. Okay, but again, the takeaway here is that we eventually were able to get a lower bound on the search problem. It's strictly less than 3/4, and so that's a separation between what you can do with truthful and non-truthful polycommunication algorithms for 2-bitters and XOS valuation functions. Okay, so again, I will take maybe just like a quick 20-second breather, and then I will go on to results in the computational model. This is, there's nothing technical in this section. I'm just going to introduce a definition and try to convince you that it's a cool definition. Okay, so let me go back and quickly remind you of this example with combinatorial public projects. So here we said this weird thing happened where this mechanism that I will call set for free, we said there's one bidder. I can give the bidder up to k items. They have a submodular valuation function, and I just want to maximize their welfare. There's one bidder. And we said this weird thing happens where if I just tell the bidder, please take your favorite set of size k, that technically this mechanism is not truthful and computationally efficient at the same time. Okay, and again, I want to go through the thought experiment of like, if I just insisted on using this mechanism where I told the buyer, pick any set of size k that you would like for free, what would I expect to happen and how robust would that guarantee be? So what I would expect to happen is I would say, well, there exists a polytime 1 - 1/e approximation. Do I predict the buyer runs that algorithm? No, I don't predict the buyer runs that algorithm. But I predict that the buyer is going to do at least as well as that algorithm, right? So they might have a different heuristic that they like better. But I would say if you're a buyer and you're presented with this mechanism set for free, there exists a 1 - 1/e approximation that runs in polytime, and you for some reason do worse than that, then I would say that's a little bit crazy and that's not robust. So I'd say it's fairly robust to just say that the buyer will do something which guarantees a 1 - 1/e approximation. And let me also point out that something the designer can do, the designer can just write up the algorithm and hand it to the buyer and say, here is some advice, just run this algorithm. If you like the set, take it. If you don't like the set, don't take it. That's fine. The designer can do that. And that will help the buyer guarantee a 1 - 1/e approximation. Okay, so what I want to say is there is something very robust about claiming that this mechanism will get a 1 - 1/e approximation, even for a computationally bounded buyer. And I just want to try and get a solution concept that captures that well. Okay, so again, what I want to point out is that the solution concept is going to let the buyer play a dominated strategy. right? So in this mechanism set for free, there is a dominant strategy, right? The dominant strategy is you should pick your favorite set, right? But we're saying the buyer can't figure out how to do that in polytime. So we're not only going to let them, we're going to let them play a dominated strategy, right? It's just some strategy that they can find in polytime. We're basically just going to say something like, okay, as long as you play a strategy, if it's dominated, that's fine. I just don't want it to be dominated by like this specific algorithm that I gave you. Okay, so let me again remind you that for combinatorial auctions, the reason this is interesting is because of posted price mechanisms, where the issue is this demand queries. And the goal of this part of the talk is just to get a solution concept which guarantees the same 1 over poly log approximation for submodular bidders. And that is at least as robust as implementation in undominated strategies. Okay, so we really want to make sure that it's very permissive and that it's the case that not only does it allow the bidders to play any undominated strategy, it will allow them to play dominated strategies and will still get a good approximation guarantee. Okay, so let me build up that definition. Okay, so to start with, think of a mechanism. A mechanism is just an extended form game. It can be randomized, but it's an extended form game. So what is advice? So I want to say the advice is, think of it like this. It's going to, for a bidder, they're going to have some action that they're thinking about taking. And the advice is going to say either take that action or here's a different action I suggest that you take. Okay, so very formally, it takes as input the state of the mechanism, the valuation of the buyer, a tentative action that they're going to take, and it's going to output a new advised action for them to take. Okay, so what does that induce? It actually induces a complete mapping from a valuation V and a tentative strategy S to a new advised strategy. So if you just apply this mapping at every single action, it'll say, oh, or at every single node, it'll say you should just take this strategy instead. Okay, so this is kind of like the, the key idea is I would say advice is useful if for all valuations in all strategies, either it's the identity. So either it just says stick with the same strategy you're using, that's fine. Or it gives you a strategy that dominates it. Okay, so in the second property is that we'd like the advice to be idempotent. So we'd like it to be the case that you can't just infinitely or unboundedly apply the advice over and over and over and over and over again and keep getting a dominating strategy. That it should just be the case that if you apply advice once, that's the same as applying it many times. Oops. Okay, so what I want to say is basically that as a player, probably you should follow the advice that's given, right? So whatever strategy you had in mind that you were going to use, someone gave you a machine that will take that strategy and give you one that dominates it. So what I would say is that what you should do, use whatever heuristic you want to come up with a strategy that you're thinking about. And then, you know what, just to do a little bit better, run it through the advice once. And it doesn't help you to run it through the advice twice because advice is the identity after you apply it twice. But you should just run it through once. It's just going to give you a strictly better strategy that dominates whatever you were doing before. And so now this gives a formal solution concept, which again, I said, we like to call implementation and advice strategies, which says that the mechanism guarantees a C approximation in this solution concept if there exists useful advice A, such that whenever the buyers follow advice A, it guarantees a C approximation, and that advice should run in polytime. Okay, so that's the solution concept. Okay, so what are the, let me again just quickly talk about this. So what are the nice properties? So certainly if you get a C approximation in implementation and advice strategies, this definitely implies a C approximation in undominated strategies. Okay, so it's at least as good as that. So why is that? So that's because for every undominated strategy, there is no way for me to find a strategy that dominates it, right? Because it's undominated. So what that means is that, because the advice has to either be the identity or dominate it, this means that every undominated strategy is something that a buyer can use while following advice. So following advice, right, that means using a strategy such that the advice is the identity on it. And the other thing that I think is nice about this is that it kind of keeps all of the computational assumptions with the designer. So I don't need to separately assume that the buyers run in polytime and that the designer runs in polytime. I say the buyers, they can, make whatever computational assumptions you want on them. The only thing I say is they need to be able to run the advice, but I don't need to make any assumptions on them being polynomially bounded or anything like that. I just need to make sure whatever they do, whatever heuristic they use, I just need them to be powerful enough to run the advice. And then the solution concept makes sense. Now on the designer, you can say, oh, I want the mechanism to run in polytime. I want the advice to run in polytime. And so this makes it much cleaner to reason about the computation because everything is just on these two things. There's the advice that should run in polytime. There's the mechanism that should run in polytime. And then you don't have to stress about the buyers. Okay, and then the last thing, I mentioned that there's this older paper which introduces the same concept under algorithmic implementation. So I'm not going to repeat their definition. I would say there is an interesting distinction that I am not going to say in 2 minutes between the cases that we use it for. But I would say the definitions are the same. The way that we use it, there is an interesting distinction between the way that they used it for their mechanism. Okay, and I think since I only have 2 minutes, I think I'm going to skip this bit at the end. But basically what I want to say is that if you are familiar with these really, really robust sounding claims for posted price mechanisms, so I think maybe Feldman, Graben, and Lucier is the first one, the first paper I'm thinking of, where for XOS bidders, there's this really robust simple lemma, which says like the welfare you get is very good because I can separately prove a lower bound on everyone's utility and separately prove a lower bound on everyone on the revenue that the auction gets. And these kinds of lemmas seem extremely robust, that you say like, okay, it actually was not crucial for that lemma that the buyer purchased their favorite set. I really just needed the buyer to purchase a set that was like not so crappy for them. And then those lemmas are really robust and you would expect them to be robust to approximation. And it turns out that that is good intuition. And there is a way sort of like this is the right formal solution concept to say, if you are using a auction like the state-of-the-art ones, where the main technical workhorse is this kind of lemma, that those kinds of mechanisms tend to be robust to the bidders not optimizing perfectly. And there's a right notion of approximate demand query that you can make, and there's a nice way to turn that into a formal notion of advice. But I guess I skipped the precise technical details for how to do that. I know that won't be interpretable to everyone, but if you're familiar with those lemmas, the main punchline is that those lemmas are really robust to approximation, and this solution concept kind of is able to make use of that. Okay. So just to quickly remind you of the results. So I gave you a result in the communication model, which was a separation between algorithms and truthful mechanisms. And in the computational model, I told you a new interpretation of this solution concept, and that it allows, and maybe the more interesting thing is applying it to combinatorial auctions so that we can kind of catch up computation to communication for the state of the art. Okay, so in terms of future work, I would say, I left the middle stuff in here was open questions related to the paper I didn't present. But the one at the top and the bottom, I would say, let me just focus on one. I would say the most interesting open problem, in my opinion, is that for 2 bidders, I mentioned that there is a 3/4 approximation algorithm we now know that there is not a 3/4 minus 1/240 approximate truthful mechanism for XOS bidders. I am not convinced that we can actually do anything non-trivial with the truthful mechanism. So I would say it is entirely possible that the best truthful mechanism in polycommunication for 2 XOS bidders actually doesn't even do better than a half. So it could be that for 2 bidders, the best polycommunication truthful mechanism is just to run a second price auction on the Graham bundle. And I think understanding, so for me, I would say the thing I'm most interested in is understanding whether that claim is true or not. So is there some non-truthful, is there some non-trivial truthful mechanism for 2 XOS bidders, or is it the case that literally the best thing you can do is just bundle the items together and run a second price auction? These are other instances, but that's the one that I wanted to highlight. So that's it. Thank you very much for listening.
Thanks, Matt. So I guess formally our time is over. So if you need to leave, you are welcome to leave. And if you have any questions, then you're welcome to ask.